So in the Bayesian game, is that we don't have that assumption anymore. We would looking at more general case where the players or agent um, doesn't have the full information. Some of the information they don't really know. And the reason they call it Bayesian game is that they can actually using Bayesian inference, using inference solutions to infer those unknown information, and from that based on that to make their optimal decision. So if you're looking at this syllabus, so we start with basic game theory, like normal phone game, with that all information that are shown that available, and we're looking at this, some of the specific case, like a potential games where those games that this payoff functions or payoff has particular structure, so that you would have a much simple representation of games. Therefore, they have quite nice properties. For example, some existence of pure Nash equilibrium, and so on and so forth. The extended form game is that we're looking at a case that you can have sort of a time-dependent case, that so this guy taking action first, and then another one based on the action go to the. So there have a few iterations. Whereas the standard normal form game is basically we assume that simultaneously take action. We're also looking at the specific case of the extended form is a repeated game. Is two agents going to repeat it many times by playing one same stage game many times, but recognize the fact that future reward would also have impact on their current decision. And when then we can talk about is given that all these concepts were introduced, and one of the concepts is obviously Nash equilibria, and then the lecture 3 is really about how to solve that. We're looking at the cases that again we know all the information, okay, and to see in that situation can we actually compute Nash equilibria, right? So today we're going to talk about is the Bayesian game is that, okay, suppose where we not know all the informations. The typical example which we're going to go is auction theory, right? In that case that we do our auction, we do the bidding, and knowing that we don't really know the intrinsic value of the item that we bid and what's going to happen. We don't really know the bids from other users. What would be our optimal bidding, what would be equilibrium, and so on and so forth. So as I said, this is incomplete information. It exists in many cases, like a bargaining, right, the auctions, and also the market competitions. That the Connell's case that we assume they know exactly cost, but we're going to looking at some cases here is that we don't really know the exact cost of our competitors and see what happens. And also we got this signal games is that how can we actually infer some information based on the signal or observation that we got, right? This signal could be someone who sent to us, or the social learning. We basically to leverage the decision of others in order to make the better decision. So like a voting and so on and so forth, presidential election and so on and so forth. So this Bayesian game, and we can looking at this example. So we got this battle of the sex game last time is a way to indicate this coordination. So we got these two actions, ballet and football. Which one are you gonna choose if you wanna, play together with your partner or with your girlfriend or boyfriend? So here, if everybody sort of coordinate together, both do this ballet event or football event, they are coordinated together, they have a much higher reward. But if you discoordinate it, and then they don't. So we know that in this case that we got two pure strategies, right? This guy and this guy, and also we got a mixed strategies, which you can easily calculate by using the rules the characteristic that we explained last time. Yeah, you can do that to figure out the mixed strategy. So now you can imagine that the player one does not know whether player two wish to meet or wish to avoid player one. So in other words, that you not necessary to have a 100% picture about the opponent's payoff. Okay, so you might have this asymmetric information. In other words, the other people might know you exactly, but you do not necessarily know the others. So let's take this example, is that you have the player two might have two types. You just don't know their types. It could be the type one that their payoff is represented like this, or the player two their payoff would like this. So player one is that they happy to go together with you, right? For an event, as long as they go together with you, either ballet or football, and they happy enjoy together with you. But it could be this player two try to avoid you, right? They could be this case that if you both of you taking action together, join taking the event together, this player two didn't enjoy it. But instead, if you bypass to each other, and then they will get a positive reward. So positive payoff. So the player two, but know which game is going to pay. So player two basically know their type, whether they're likely or not. But player one does not know. So in this case, what are the strategies? Right. So that's the question we're gonna ask. So suppose that they actually have some sort of estimation about the types. So let's say you got this. If I know this player two has a 50% of chance falling into this normal phone game with me, and also 50% of chance, play this normal phone game with me. What should I do?
Maybe you can take the expected value of the player two payoffs. So here you would just take the mean for each cell. Yeah.
So basically, you sort of come with this kind of inference with uncertainty. This uncertainty is captured by this 50%, right? Therefore, you can calculate the expected payoff to see which one will be. Yes. So for player one's viewpoint, player two has two possible types. Then reason about this equilibrium is that using large equilibrium concept in the expanded game, where each different type of players who has different strategy, and then form the beliefs about others' action in this state, act optimal. Yes. So that's basically this how to do that. So then we can consider this the sort of a strategy BF. So here the notation is that for player one, this is sort of their pure strategy. For player two, they actually got this two pure strategy. The first one is basically say, okay, given state one, right? This remember the normal phone game on the left, and I would take an action B, and if on the normal phone game, is it on the right? I would take football as my answer. So clearly, given the play of B by player one, the strategy of player two is the best response. How can we verify this? Given the player player one play B, why BF is the strategy of player two? Why BF is the best response strategy for player two? If the play left, right, then BB is sort of nobody gonna deviate. So they don't want to deviate from it, isn't it? If you want to deviate from it, then obviously you would from 1 to 0. They don't want to deviate from it. Equally, you can double check the F as well. Yeah, so we can also to verify that from player 1's perspective, what's gonna happen? Whether play 1 is also our best response. Okay, you can actually looking at this expected payoff. Given the BF, and also given the BF, if I have alternative choice, which is F. Okay, so you can actually calculate that the B give you expected the highest expected payoff against the, if player 1 gonna choose F. So you can see that. Therefore, the strategy profile BBF is a Bayesian Nash equilibrium. So fulfill the definition. I is the best response of you best response of me, and therefore it's a Nash equilibrium. So noting that meeting at football, which is the preferable outcome for player 1, is no longer a Nash equilibrium. Why not? So this meeting at football is preferable outcome for player is no longer a Nash equilibrium. Why? Suppose the two players will meet at football. When they want to meet, then the irrelevant profile is F. Yes, FB. If player 1 deviate and player B and deviate and play B irrespective of would be so. Therefore, strategy BF is not there. So I think it's already written here. Therefore, the strategy BF is not Bayesian equilibrium. Yeah. So I think what you do here essentially is to because of uncertainty, you use that uncertainty marginalize this uncertainty out, right? On that random variable out, get the expected value, and to see whether that's the best response or not. So that's basically how to. Let's see how formally we define this. So we still same thing as before. We have set of players, and also we have a set of actions. The same thing for each of the players. The different things here is that we have theta I for each of the player, which indicate their type. And that utility or the payoff not only depend on the joint action, but also depend on the types, right? For each of the agents. So each agent has their own types, and this utility also depend on that. And also you have, because it's a Bayesian game, and you have tools to sort of model your uncertainty, right? Because you have incomplete information, therefore you can actually have estimation of that. In this case, types. And these types can using probability to indicate your uncertainty associated with that. So, and then normally one could allow for a signal for each player. What does it mean? Signal is that I could give you some additional information. So you got this sort of types distribution, right? Suppose you have additional observation, like for example, could be something X you observed. As long as it's a certain distribution, then you would be able to have a better understanding of the types. Or you might have this sort of opposition or I, theta J. Then, for example, you know your types, and if the types are correlated, therefore you can have a better estimation rather than sort of the prior distribution that you've got. So this could be the case. So you got this strategy space, payoff space, possible types, and prior information. So we would actually assume they are the common knowledge. In other words, this prior distribution, everybody knows that. So it's a strong, definitely very strong assumption, but it's very mathematical convenient. We can using this to do that. And the pure strategy is basically that for each of these types, right, that you have, and to really to figure out your sort of strategy. So think about this, that suppose this player one, in this case, you don't have a type. Basically, you have just type one type, let's say. And this player two has two types. Therefore, each of the type, they have decide have this sort of which action they're gonna take. So then this added together is their sort of a pure strategy. Okay. So this is what I said. You basically use sort of types you can influence others. And so mathematically, you could write it down, this utility or this called expected, so-called expected payoff by marginalize all this uncertainty out, right? So you got this individual utility payoff depend on the types, right? Depend on your action you're gonna take, right? And then suppose obviously you know your own types. Given your own type, you have estimation of others, and these are the policies from others, right? Given their own types, what kind of strategy they're taking, and because you marginalize these types out, then you got the expected utility, which only depends on your action, your opponent's action, and also your own types. But of course, if it's a continuous variable, then you can use this sort of integration out. So that's the idea. The equilibrium is basically the pure strategy. As I said, this pure strategy depends on each of your types that you got. Is to really maximize that expected payoff, you expected payoff, provided that the strategy from others they are also in equilibrium as well, right? So the Bayesian Nash equilibrium is a Nash equilibrium for the expanded game in which each player I space of pure strategy is a set of mapping from this, as I said, sort of from theta to Si. So it's expanded game, right? Because that you have different multiple types. For each multiple type, you need to figure out the what sort of a strategy action you're gonna take. So this there's some theory behind it. So given the limited time, we're not gonna prove that, but the finite encounter information game that there's always exists a mixed strategy Bayesian Nash equilibrium. So that's a theorem. So we can looking at this, understand the concept now. I think what we just to understand a bit more is just looking at the Cournot case again. Okay, the Cournot, the nice thing about Cournot model is that you can modify it, and then based on the modifier, you can draw different conclusions. In this case, we basically can modify it. Say, suppose you don't really know the opponent's cost. Okay, if you don't know, but you know is that they have certain probability of cost error, right? Low cost, or you can have some probability of high cost. Based on this, we'll see what this Cournot model would give us, and the rest would be the same. So you can write this saying utility of player one is the same, right? Because they have a fixed cost. Utility two is different now, is that we don't really have deterministically know 100% know the cost, but rather say this is a CT, okay? And this random variable has theta probability being CL, and also have a 1 minus theta probability being CH. We'll see what happens. The rest will be the same. We'll see what happens. So in this case, you could write it down. A strategy represent as this, as the following, as we said before, right? You basically have this. You for player one, you still have Q1 star, right? And then for player two, you basically have is that QR and QH, right? Or write it down in a more formal way. Given different type, you have different sort of decision. So mathematically, then you could write this so-called best response function. So the best response function is that, okay, for player one, for player one, and the input would be QR and QH, isn't it? QR and QH is this is a policy that they're gonna have for player two. And you can write down this for player two. Then you got these two pure strategy, right? One is that what happens when your cost is QR, and then another what happens if your cost is QH. So you couldn't do that. You've got three variables and three questions, three variables. You can solve it. So this is actually the solution you got. In a linear solution, we can actually get this. So I think that's sort of the explanation on that. I think you can actually read some when you have more aggressive case, what's going to happen when you don't, given the cost. So this is sort of a incomplete information. And another example is auction. Okay, so this is sort of a very important application of Bayesian game, and it's because it's been widely used. In fact, this year, or not this year, last year, Nobel Prize was given to the two professors who are very active in this auction theory. So this is very important.